That's future 2 is good. Yep. Four-dimensional figure. Oh, you good. That's good. Okay. I scared you of math. Looks like I scared you of English too. All right. All right. So today's awesome. You guys are gonna love today. Are you ready? You gotta like ramp up and yeah. I don't care. I'm just gonna teach. All right. Y is equal to f of x. Forget f of t. And I am going to describe a couple lines here. This could be at x. This is at x plus h. I'm going to write a secondary function. And the secondary function is going to be a of x. A of x refers to the area bounded by the curve f of x and x plus h. What is the distance between x and x plus h? H. As h increases, according to the drawing, what happens to a of x? It increases as well. As h gets smaller, what happens to a of x? Yes. So, a of x, that region right there, is going to be equal to, I'm going to write an expression for the entire area here. Okay. That'll be the area bounded from 0 to x plus h of f of x dx minus, if I want just this part, what would I have to subtract off? 0 to x. So I'm going to subtract off the integral from 0 to x, f of x dx. Everybody okay with that? All right. Now, there we go. Okay, now I'm going to draw a rectangle. Would you agree that the area of that rectangle is approximately equal to a of x? Approximately. In fact, as we drew x plus h closer to x, wouldn't they be even more and more similar? As x plus h moves closer to x, so what would h be moving towards then? 0, right? So we won't write the 0 part first. We'll just write that expression. Approximately a of x is equal to the area of that rectangle. What's the width of the rectangle? H. What's the height of the rectangle? F of x. I don't like the h over there, so I'm going to get rid of it. How do I get rid of it? Somebody, how do I get rid of it? Divide it off. I'm going to leave some space here. Probably because I want to write something there. Jeez. Who invited you to class today? Look like a All right. Now, would you agree? Would you agree that a of x and h times f of x? So the red triangle and the blue area, would you agree that those would be even more similar as h approaches 0? Does this look familiar? Okay. Right now is the aha moment, okay? All right? Are you ready? Okay, so don't write anything, just watch, okay? Yeah. Doesn't that look similar to we used that first semester, didn't we? To do what? To find the derivative. This is the formal definition of the derivative, okay? Now, I've got something very important to show to you, okay? Suppose that my function is equal to x squared. Then I would have the limit as h goes to 0 of x plus h squared minus x squared all over h. What will you get out from that when you do that? What will the result be? 2x. You're going to get the derivative of the function, correct? So if, okay, this is the step. This is the logic. You guys got to try to follow this if you're going to make any kind of step here with the next part. If I write this, limit as h goes to 0 of sine of x plus h minus sine of x over h, what do I get over here? Cosine. Because you recognize that the function was sine, so the derivative was cosine. Function was sine, derivative was cosine. Look at your next part. Look at this spot right here, okay? That means the function is the area function, right? The integral. The function is this integral thing, and the derivative is f of x, okay? Statement about f of x. F of x is the derivative of the integral function. Yeah. So f of x is the derivative of the integral or area function. So hold on. So that means if I had, okay, watch this. This is the last step you got to make. If I had 8x squared over on that side, what would I have over here? 16x, right? Well, what if I have x squared on this side? What would I have over there? Okay, we'll make it easier. What if I have 3x squared over there on that side? What would I have over here? X to the third. You would have the antiderivative, right? That tells us if f of x, if f of x is the derivative of the integral, that means that the integral is the what of f? Is the antiderivative, right? Did you hear that? Did you see that? We'll try it again. I will in a second. Okay? If cosine of x is the derivative of sine of x, okay, then that means sine of x is the antiderivative of cosine, correct? That's the statement we're making. So therefore, if f of x is the derivative of the integral or area function, then the integral area function is the antiderivative of f. The area function is the antiderivative of f of x. This is amazing. Okay. We need to learn fundamental theorem of calculus part 1. It's a little bit more confusing. We're just going to learn part 2 today. Okay. Seems kind of opposite, but often it's taught in that order. Okay. Let's first talk about antiderivative, and we'll talk about evaluating the integral. First of all, what's the antiderivative of x to the n? Yep. So we said that we'll use large f of x to represent antiderivative. Yep. We're going to bring it back up. That's what you guys did a day that I was gone. We bring it over to here. So antiderivative of the following. What's an antiderivative of x to the third? What's the antiderivative of 5x to the fourth? X to the 5x to the fifth over 5. They cancel, just x to the fifth, correct? Next one. 4x to the over 7. Now here, f of x is equal to 3 over 2x to the negative 3. So what I'm going to do is I'm going to add 1 to the exponent and divide by the new exponent. Three over 2x to the divided by negative 2 over 1. How do I simplify that? I multiply by the reciprocal. So f of x is equal to 3 over negative 4x squared. So what we learned on the previous page is that we need to use antiderivatives. Why? Because the area function is the antiderivative of f of x. So therefore, what this means is if you want to evaluate this beast right here, it used to be that we took limit of Riemann sums as n went to infinity, okay, and we added up the area of an infinite number of rectangles. Some of you guys are still practicing that. Some of you guys haven't done a problem yet. Some of you guys have done all 8. Wherever you're at, you need to know how to do that for the test, okay? But got to be able to do those problems. Area bounded between a and b of f of x dx is equal to, how do we do that? We simply find the antiderivative of f, and we evaluate b minus the antiderivative of f evaluated at a, where f is any antiderivative of f. So now that's all we need to do to evaluate the area. It's so easy. So watch. The integral from 0 to 2 of x squared dx. Don't worry about the dx. We'll talk about what that means later on. But as we have, well, I'll show you what the dx is. Look it up there. You see the limit, Riemann sum? See how we got the delta x? The delta x is like the dx. Dx is like the width. Infinitely small width, okay? That's what's happening. And so we keep it there until we take the antiderivative. So, trust me, we'll get a better explanation later. So 0 to 2, that's what the graph of x squared looks like. So we want to know that exact area. And I told you the other day I could look at it and I could see it was 8/3. Well, here's why. What's the antiderivative of x squared? Evaluated from 0 to 2. So we draw a bar and you put your upper bound up top, your lower bound on bottom. That's how we evaluate integrals. That's what that means. So let's plug in 2, 8 over 3, minus, plug in 0, you get 0 over 3, so 8/3 is the exact area. That's notation we will now use. You'll use it all the time. A bar. Sorry. I'll try to change mathematics for you so it works out. She's being sassy. Sine bar? You're just so funny today. Not just funny looking, you're like funny. Oh, now we're making you laugh. Okay. All right, let's do another one. Look at this, 3x squared. From 2 to 4. We want to find that area. Okay? Well, what's the antiderivative of 3x squared? X cubed. We evaluate it at 2 and 4, and we subtract the results. What's 4 to the third? Minus is done. Maybe. Get out of town, folks. Come on back and be ready to go. We do C together. We can even do square root functions. So if f of x is equal to 3x to the 1/2, what is big F of x? 3x to the 3/2 divided by 3/2. And if you multiply by the reciprocal, you'll get 2x to the 3/2. We have 2x to the 3/2 evaluated from 1 to 2. When we take 3x to the 3/2 divided by 3/2, we multiply by the reciprocal, we'll get 2x to the 3/2. Okay? So we plug in 2. What is 2 to the third? 8. What's the square root of 8? 2 roots of 2 times 2. Roots of 2 minus, now we plug in 1. So this is the exact area. Now on the test, if I ask you to compute stuff like this, I would expect that you write it in simplest radical form. I know you could come up with a decimal. You simply just do second calculator on your calculator, right? So that's not as impressive. Make sure that you list the exact amount, okay? D, all right? Now, here's what's interesting about D. I want you to take D and graph it on your calculator. Or you can just watch mine, x to the third minus x squared plus 2x minus 3. Okay, so I want you to look at that. See the shape? From 0 to 1. Is most of it negative or is most of it positive? Yeah, in fact, if you draw the rectangles, if you go 7 and then you calculate from 0 to 1, you can see, oh, it didn't even, whoop. Yeah, you can see it's actually all underneath, isn't it? So now that I put it there correctly, I didn't have my window corrected. But so you can see that there's nothing that's above. Everything's below. So is this area going to be positive or negative? It's going to be negative. So we take the antiderivative. What's the antiderivative? X to the third. X to the fourth over 4. Antiderivative x squared. X to the third over 3. X squared minus 3x. When we plug in 0, what will we get? And when we plug in 1, it looks like we're going to get a fourth and a third, so I'm going to convert everything to twelfths. So 1/4 is 3/12 minus 4/12 plus 12/12 minus 36/12. 3 minus 4 is -1 plus 12. 11 minus 36 is -25. And as you look, -2.083 repeating is -25/12. It's just think of how long that would take us to do that problem using the area of an infinite number of rectangles. That would be difficult, wouldn't it? And we did that very, very quickly. Yes, I have an answer. That's correct. Negative area is a thing in mathematics, and area is sometimes a bad representation, or a bad word to talk about that. But accumulation. You know, for example, you can have snow accumulating and snow melting. So snow melting would be area above, right? Because you could actually have 3 inches of snow falling, but 1 inch of it melted right away, so that when you look at the end, you have 2 inches. Well, you need to calculate the, you see what I'm saying? So there's different situations in life where we look at that kind of net accumulation. So, all right. But, okay. Laughing attack, Emerald and Amber. We're not continuing until you tell us what's going on. That's hilarious. Did you find $5 then? Oh, okay, that would have been great. Okay. All right. Emerald, we get you done hiccuping then. Very good. If you do it again, you just leave. Okay. All right. Sine of X. You should know what the graph of sine of X looks like. Its period is 2 pi. And we're looking at the area bounded between 0 and pi. So is that area going to be positive or negative? Positive. What is the antiderivative of sine? Negative cosine. Most people, when you ask them the antiderivative of sine the first time, they say cosine. Well, wow. Good job, Matthew. Yep. Matthew never makes mistakes, so let's just make sure we understand. All right. All right. Cosine. What's that? Oh, I did last week, right? I didn't? Oh, I'm sorry. I showed second hour. Okay. All right. I'll show you guys. I thought I did. All right. What's the cosine of pi? -1. Make it negative, so +1. What's the cosine of 0? 1. And then make it negative. -1. So this area is exactly 2. It is. Just units. And then the last one. This is 2x to the -2. What is the antiderivative of 2x to the -2? So that's the area. That's what the graph looks like in that region. As we evaluate it, we plug in 5, we get -2/5 minus -2/1. So -2/5 plus 10/5, and we get 8/5. What do you think? Okay. Well, how about this? Regardless of whether you like this or not, this is something you will have to become excellent at, because we are not just going to do. Okay. I want you to know, as we move forward, everybody, a couple things. This is really important. Um, First of all, we're going to take this kind of a shape, and instead of finding the area bounded between the curve and the x-axis, we'll find the area bounded between two curves. And then after we do that, what we'll do is we'll take this shape and we will swing it around the x-axis to get a three-dimensional shape that has space in the middle, and we'll find the exact volume. So we're going to do a lot of stuff. It's very powerful as we move forward. Last of all, I just want you guys to see this. What is the antiderivative of 3x squared? Very good. So, how about this? How about x to the negative 1? X is 0 over 0? Is that what you're going to do? Can't divide by 0. Do you remember from first semester what you take the derivative of to get 1 over x? Natural log. So, here's the point. The point is that finding derivatives is actually pretty elementary for calculus. You guys had a test first semester. At the end of the semester, it was your final exam. Find the derivative of anything. Finding the antiderivative of anything is actually pretty difficult. Yeah, yes. You have to be able to find the antiderivative of anything for your next final. I should say of anything. There are antiderivatives out there that are extremely complex to find. We would have to know much more about calculus 2 and other subjects in order to do it. So, but that's kind of the point. So, have you ready to go? So, if you look at your very last page, there's a worksheet, and there's 12 problems. You need to sketch the graph and find the area. You can check that on your calculator. That's your assignment. Go to work.